on a force. So then accordingly, you will be getting some electrical voltages or charges. So that is active transducers. Okay, that is called transducers. And why it is called that inverse transducers? Because that there is opposite, because it also transforms the one form energy to another form of energy. That means if we supply some any voltage signals, if we apply some any voltage signals in the crystals or materials, okay, piezoelectric crystals, so then what will happen? So it causes some mechanical vibrations. So mechanical vibration means some displacement, some there is a mechanical mechanical energy. Okay, we convert to electrical energy to mechanical energy. So that's why it's called that is the inverse transducer. So piezoelectric crystals transducer property is that that is it is known as the active transducers, and as well as that is inverse transducers. So that is the main properties. Okay, so that is the main properties, the piezoelectric transducers. Okay, so active transducer in the case why it is called the cell generating device, and that is a force. It converts the force to voltages or electrical charges. Okay, so that is a transducers. And inverse transducers means if we apply some voltages, then it will be getting some mechanical vibration, some displacement, some mechanical energy. Okay, so that's why it is known as the inverse transducers. Okay, fine. So now that actually in our daily life that we are dealing with piezoelectric transducers, piezoelectric sensors, because that in case of microphone, okay, it is used in the microphone. That in the microphone, what is the mechanical? That is a sound pressure. Okay, that is a sound. Okay, sound energy. That is the pressure. So so that is a converted to the electrical signals. Okay, and now the signal is amplified to produce the louder sound. Okay, so that's why. So that is that is a use of the microphone. That is a piezoelectric crystal that is used here in the microphone. In our that second application daily life, like lighter in kitchen, lighter. Okay, so lighter means the inside a piezoelectric crystal is there. So when the pressure made on the piezoelectric sensors, when we put some pressure, lighter होता है ना जो हम press करते हैं, so pressure made on piezoelectric crystal, so then what will happen? Create some electrical signals. Okay, inside it creates some electrical signals. Okay, so that causes that that flash to fire off. So that is a lighter function of the lighter in kitchen. Okay. So that is the inside it that piezoelectric crystal is there. So this is one daily life application. Okay, that is another application. Restaurants, airports, shopping malls, there are piezoelectric crystals that is used also. We have seen also, we have experienced that when we step near the door, then what will happen? When we step near the door, actually what is happening? That it opens automatically. Okay, sir, it opens automatically. So in this concept, this concept is used. This piezoelectric concept is used because when we are near the door, so pressure is exerted. Okay, so pressure is exerted means our weight. Okay, our weight. Okay, there is a person weight. Okay, that on the sensors. So due to which now some electric effect is produced inside it. Due to which inside it the electric effect is produced. So that's why the door opens close automatically. Okay, so that is a daily life application. So we're dealing with some piezoelectric crystals. So there is so many applications where the piezoelectric crystals is commonly used. Okay. Otherwise, the industry purpose use use, and that is recently that it is researchers that doing research that on piezoelectric crystal in medical diagnostics and infertility treatment. There is a very challenging area right now. There is infertility treatment in the medical. Okay, so that is why the piezoelectric crystals, transducers is being used nowadays. Okay, so it is developing. Okay, so it is developing. So that is actually that is a point of care method. Okay, there is a point of care method. That is a there is a chip. There is a single chip inside on it. That piezoelectric crystal will be inserted. Okay, there is a point of care method. So actually it is acting like a smart sensor. Okay, a smart sensors or transducers. Okay, so in the medical purpose that it is being used right now, it is a challenging task nowadays. Medical diagnostics purpose, infertility treatment. Okay, infertility treatment is a very challenging task nowadays. Nowadays. So So this is a very common application, and this is daily life application that basically that we are dealing with the piezoelectric transmission in so many areas. Okay, so and piezoelectric, piezoelectric crystals, transducer, that is a high sensitivity. Sensitivity is very high, so it acting as a sensor. So that's why it is used in a accelerometer also. Okay, accelerometer in this case of measure of the acceleration. Okay, that is measure of the acceleration, measure of the vibration, whatever. So as it is a high sensitivity, okay, so that's why it is used as an accelerometer due to its excellent frequency response. Okay, excellent frequency response. So that's why piezoelectric crystals will be used as a accelerometer. Okay, piezoelectric crystal. So these are the basic applications, the basic properties, and these are actually the materials. Materials basically, two type of materials basically may be used for the piezoelectric transducers. One is that natural, one is the natural, another one is that synthetic. Okay, so just network. Okay, so artificial basically that is a synthetic group, that is a ammonium diphosphate, beryllium, potassium nitrate, lithium nitrate. Okay, so these are the materials that fall under the category of the artificial group. Okay, means synthetic. Okay, so natural synthetic group. So mostly basically the quartz is preferred. Okay, there is a quartz crystal is preferred mostly, the quartz crystal, because these materials provides the basically high frequency response, high sensitivity. So these are the properties of the quartz crystals. So that's why the quartz mostly that is a preferred. Okay, natural metals that is a preferred quartz. So this is basically the definition. This is the the definitions and the basic properties. This is the application of the piezoelectric crystals transducers. So next, the working is very simple. The working that is a very simple. So that is this is the 4 diagrams that I have included here. So actually, what is the piezoelectric crystal? So right now, just I have said, suppose this is a crystal. This is a crystal. Okay, so if we apply some pressure, if we put some pressure on it, if we put some pressure on it, means it's squeezed. Okay, when it's squeezed, then it will develop across its surface a charge. It will produce a charge. Okay, so across the surface it will produce a charge like that. Across the surface it will produce a charge. Okay, so now actually this charge, that is a Q. This is the charge. That is a Q. That is nothing but a the function the function of this input pressure or input force. Okay, so charge can be calibrated in terms of this input quantity. Okay, so now actually this charge level is very low. Okay, the charge level actually is very low. Okay, very low level. So that means that the signal is very weak. Okay, so you have to get some high level of voltage. Okay, you have to increase the strength of the signals. Okay, to operate it. Okay, so now what you have to do? So across the piezoelectric output, okay, this charge output, that would be taken into the through the amplifier. Okay, it's taken through the amplifier. So that is known as actually charge amplifier. Means it amplified the charge. Okay, that is amplified the charge. Okay, amplified the charge means the signals will be getting some high level of signals. You'll be getting high level of signals, low to high level. So that's why the amplifier is given. That is the amplified. Okay, that is the amplified. So that is the function of the amplification. Okay, so in the in this diagram, I have already shown the I have already shown the equivalent circuit diagram. So this is not equivalent circuit diagram actually. Okay, so this is the equivalent circuit diagram. This is the piezoelectric crystal sensors. Okay, so charge is carried out in a charge in an amplifier. Okay, this is the amplifier, electronic circuits. Okay? So this electronic circuit is the amplifier, charge amplifier. Okay, so there's some open circuits and whatever, open differential amplifier, whatever. Okay, and there is some filter is there. Filter is added. Okay, there is some to reduce some noise, to eliminate some noise. Okay, so the signal should be processed. Okay, through the filtering. It should be filtering. Okay, so that is actually the electronic circuit is equivalent, electronic equivalent circuits. Okay, that is the electronic equivalent circuit. So here you can see this diagram. So actually crystal is placed between these two electrodes, and when the the pressure is applied, then accordingly what will happen? That charge is produced. Okay, so it may be compressed and it may be tensile tensile stress or compressive stress may be acted upon it. Okay, so this is a tensile and this is the compress. This is a compress. This is a tensile stress. Okay, so accordingly charge will be developing. Charge will be developing. This charge is taken to the amplifier because why? Because this is a very low level signals. Charge is the level is very low level. Okay, so that's why you have to increase the strength of the signals. Okay, so that's why amplifier actually boosts the signals, means you will be getting some high level of power signals. So that is an amplified output. So that is actually the piezoelectric crystal properties inside it. Should be amplifier, charge amplifier should be included across the output of the piezoelectric crystals. Okay, and this is actually this diagram. This is the inside the crystal axis. Actually, cut away view. Okay, this is actually the cut away view. Okay, so actually x-axis. This is the x-axis and this is the y-axis. This is the x-axis. This is the y-axis. This is the x-axis. This is the y-axis. This is the crystals. Okay, cut away view actually inside the crystal. Actually, that some electrical stress and mechanical axis, electrical axis and mechanical axis. Actually, we are considering in this way. What is the electrical axis and the mechanical axis? Okay, so that when the electrical stress applied in the direction in the electrical in the direction some electrical axis, suppose x-axis. Okay, so a mechanical strain is produced in the direction of y-axis. Okay, mechanical strain. Okay, similarly, if some mechanical strain is given along the y-axis, so electrical charges will be produced to the face of the crystal along the x-axis, because x-axis and y-axis the perpendicular actually. Okay, that is the perpendicular. So inside the crystal, this is the crystal. Inside, this is actually cut-away view. So that's why I have included this diagram, cut-away view, inside diagram into the crystals, x-axis and y-axis. Okay, because crystal actually there is a combine of the mechanical and electrical energy. Okay, it is follows because it is acting as a transducer as well as inverse transducers. Electrical to mechanical and mechanical to electrical. Actually, it is happening inside it like that. Okay, so there is a cut-away view, crystal axis, x-axis and y-axis. Okay, it is not so too much important. This is the inside view. Okay, this is a cut-away view. So this is actually the basic schematic diagram of the piezoelectric crystals, and this is actually the equivalent circuit diagram. Okay, so with the charge amplifier, when we apply the charge amplifier, then what will be the we will be getting the output. Okay, and another thing is that suppose here we are getting voltage. Okay, we are getting the voltage and then to the charge amplifier. Okay, so now what we can write here, you can write that is F, that is proportional to F, that is proportional to Q. Okay, F is proportional to Q. Okay, that means charge that is proportional to this force. This force means there is a pressure. Okay, there's a pressure. So now what is the F actually? F we can write here D into Q. Okay, F right here D into Q. So what is the D actually? D is nothing but a charge sensitivity. Okay, D is nothing but a charge sensitivity or charge density, you may know as. Okay, charge sensitivity or charge density. The density. So F equals to D into Q. Okay, F equals to D into Q. Okay, so now what will happen actually? So now actually what is the D actually? D actually is charge sensitivity. This charge sensitivity actually it is very direction sensitive. It is a direction sensitive. direction sensitive, direction dependent, that means suppose this is your crystals, okay, this is your crystals, right? So now suppose if we some force apply on it, okay, so if we force some in this direction, different means different direction, if we force some in this direction, if we apply the force in this direction, if we apply the force in this direction, so in the different direction the charge will be charge sensitivity will be generating, okay. Suppose in this direction the charge sensitivity will be generating in this way. So that suppose this is your F11, this is your F11, force is a F11, okay, force is a F11, and your charge sensitivity is a D11. So direction sensitivity, so in this direction we are applying the force, so in this direction the charge sensitivity will be generating, in this direction we are applying the force, okay. So suppose this is the F12, so charge sensitivity, charge density will be generating in this direction, so that is D12. So in this direction we are applying the force, okay, in this direction you are applying the force, okay, F13. So the charge sensitivity or charge density, that will be it will be showing in this direction, it will be generating in this direction, that is D13. So actually direction dependent, okay, very sensitive, direction sensitive, okay, sensitive, okay, that is a charge sensitivity, charge sensitivity, direction sensitivity, okay. So that is the directional dependent, actually you can say that is a directional dependent. So now suppose any question comes that how to find a resultant, okay, resultant, total charge charge density, charge sensitivity, then how to calculate it. So how to calculate, so that is nothing but a D, what is the formula, that is equals to root over of, that is equals to root over of D11 square, okay, that is equals to root over of D11 square plus D12 square, okay, plus D12 square, okay, plus D12 square, okay, plus D13 square, so on, okay. So that is actually the total resultant value of the charge sensitivity. So D equals to the resultant value is root over of D1 plus D2 plus D1 square plus D2 square plus so on. So this is actually the formula of the charge sensitivity or charge density. Okay, so this is a direction direction dependent. So if we apply in this direction the force, so in this direction the charge sensitivity will be generating. If we apply the force in this direction, so in this direction the charge sensitivity will be generating. Okay, so if we apply in this direction the force, the charge sensitivity will be generating in this direction. Okay, so it's a direction sensitive actually. Okay, so that is the function of the charge sensitivity or charge density, you can say. So that is the main property, that is of piezoelectric crystals, transducers or piezoelectric crystal sensors, whatever. Okay, so now actually how to find out now the electrical voltage. Electrical voltage means there is a V. Actually you have to find out the V. Okay, you have to find out the V, because you are applying some forces, you will be getting some output voltages, okay, electrical voltages. So you have to calculate, you have to you have to show the mathematical equations of the EMF, electrical voltage, as well as the charge sensitivity. Okay, so you have to show it. So what is the derivation actually? So first thing that we have already know, that is a Q proportional to F. Q proportional to F, the charge, that is proportional to the input force, okay, input force. So what is the Q? Q is, that is equals to D into F, okay, D into F. See the equation, D into F. So this is the first equation. Q equals to D into F, right? So now, what we know, that is Q equals to what? Q equals to CV. We know that Q equals to CV. Okay, Q equals to CV. So we can write here. CP into E. Okay, CP into E. What is the E? E actually your voltage. So this should be determined, E. Okay, and what is the CP? CP is nothing but a piezoelectric capacitance. That's why I represented as a P. C suffix P. Okay, because it is a piezoelectric capacitance. So that is why Q equals to CP into E. So this is your second equation. Okay, this is your second equation. So first equation equal to Q equal to DF. Second equation we can write here Q equal equal to Cp into E. So now what is the Cp? Capacitor means what? You have studied in the you have studied in the capacitive transducers. Say capacitor is equals to epsilon A divided by epsilon A divided by T, epsilon A divided by T. So now D, epsilon A divided by D, okay, we know that, but what is the T actually? We are representing here T. T means is nothing but a thickness. Okay, T is actually the thickness, means this is the crystals. Okay, this is the this is the crystals. Okay, this is the crystal, this is suppose the piezoelectric crystal, and this is actually the thickness. Okay, this is the thickness, that is a T. Okay, this is a T. So this is the T, actually the thickness value. Okay, so that's why the epsilon A by T, epsilon A by T, that is a Cp. Okay, so Cp equals to epsilon A by T. So this is your third equation. Okay, so this is your third equation. The first equation equals to what? Q equals to df. Second equation equals to what? Q equals to Cp into E, and third equation equals to Cp equals to epsilon A by T. So now what we can write from the second equation? From the second equation, what we can write? Because you need to find out the value of electrical voltage. So that is equals to E. So E equals to that what? E equals to then Q by Cp. Okay, E equals to Q by Cp. Right? So now what is the Q? What is the Q? Q Q is what? Q is that is equals to nothing but a D into F. Okay, E is nothing but a D into F. Okay, and what is the Cp? Cp equals to epsilon A by T. So if we divide it, so ultimate expression will come df into T divided by epsilon into A. Okay, df into T divided by epsilon into A. So now this is the final expression of the electrical voltage. So E equals to what? E equals to D into F into T by epsilon into A. So in this equation, from this expression, what we can say? From this expression, what we can say? We can establish a relation. So that is E proportional to F. That is E proportional to F. Okay, so more amount of more amount of more amount of force or more amount of pressure that causes more amount of electrical voltages. Okay, if you apply the more amount of force, more amount of pressure, so accordingly you will be getting the high output voltages, electrical voltages. Okay, so that is E proportional to this EMF, that EMF voltage. So that is proportional to input pressure. Okay, so now what is from this equation? E equals to D into F into T by epsilon by A, epsilon into A. Now from this equation, what we can write? We can write here the field. We can express in terms of field also. So that is equals to E by T. Okay, that is the E by T is nothing but that is a field. Okay, so that is equals to what? So that is equals to D into F. D into F divided by what? D into F divided by epsilon A. D into F divided by epsilon into A. Okay, so this is actually the electric field intensity. Okay, field, that is the electric field. So that is the E by T. Okay, that is the E by T. This is the expression. Okay, this expression. Suppose you want to find out the electric field. How to find out? The E by T you have to calculate. Okay, so that is a D into F. D into F divided by epsilon into A. Okay, just you have to divide by T in denominator. So that is a electrical field. So that is equation number 4, and this is equation number 5. Okay, this is electrical voltage, equation number 4, and this is equation number 5. Okay, E by T. So now again, what we can write? See, F by A means what? F by A means what? F by A means you can write is a pressure. Okay, so you can write is pressure. So now what we can write here? D by epsilon into P. We can express in this expression also. So dy epsilon into P, right? Okay, because P equals to F by A. Okay, so now this term actually d by epsilon. Okay, d by epsilon. This term actually it is nothing but a voltage sensitivity. Okay, it is known as a voltage sensitivity, and that is represented by G. That is represented by G. Okay, so G equals to nothing but a voltage sensitivity, that is nothing but a d by epsilon. Okay, d by epsilon. Okay, so d by epsilon. Okay, so and what is the epsilon? What is the epsilon? How do you can express the epsilon? Epsilon means what? You know, d by what? Epsilon means epsilon naught into epsilon r means absolute permittivity. It is the absolute, you know, permittivity and the relative permittivity and the relative permittivity. Okay, absolute permittivity and relative permittivity, that is equals to, you know, epsilon. So G equals to what? D by epsilon. This is the voltage sensitivity. Voltage sensitivity. Okay. So now here E equals to what? D by epsilon. So D by epsilon, what we can express here? D by epsilon we can express here G. D by epsilon here you can express that is a G. Okay, G into T, that is a thickness, into T. Okay, into what? Equal to F by A. So F by A we can express into F P. Okay, into P. So that is equals to E. So we can simplify in this way also. We can simplify in this way. Okay, in terms of, you know, voltage sensitivity. Okay. So E equals to what? E equals to G into T into P. So this is the final expression. Okay, it may be simplified. Okay. So this is actually the output voltage calculation. So first step is what? First step is Q proportional to F. Okay, charge proportional to force. Charge equals to what? D into F. This is your first equation. D into F. Okay. So D is, we know that this is the charge sensitivity. Charge sensitivity. D into F. First equation. Second equation what? Second equation Q equals to Cp into E. Okay, because you know that Cv, Q equals to Cv. Okay, so Cv, so C means what? C means here piezoelectric capacitance. So that is say it is represented as a Cp, C suffix P into E. Okay, equals E means you can represent is V also, but why I have represented E? Because it is induced EMF. So in that case, so that's why I am representing it as a E. Okay, so that is Cp into E. Okay, second equation. Third equation is this one, that is Cp equals to, you know that, epsilon A by T. Okay, there is a Cp. Okay, so now what we can write? E equals to what? E equals to, go back to the in this expression now. E equals to what? Q by Cp. E equals to what? Q by Cp from this equation number 2. Okay, so what is the value of Q? Just put the value. Q equals to D into F. Q equals to D into F. Okay, and what is the value of Cp? Cp equals to, you know that, epsilon A by T. So if we arrange the equation, so then D into F into T by epsilon into A, that is equals to E. That is equals to E. So now, what is the D by epsilon? D by epsilon, actually this term represented as a voltage sensitivity. Okay, and it is represented as a G. Okay, it is known as a voltage sensitivity, D by E. This expression, okay, signifies the, you know, the voltage sensitivity and represented as a G. So we can put the G here. Okay, D by epsilon replaced by G into T. F by A means what? You know, there is a pressure, force per unit area. So that is G into T into P. So E equals to what? E equals to G into T into P. So this is your final simplified output voltage expression, okay, of the piezoelectric crystal transducers. Clear? Clear? Okay, so this is the mathematical derivations. These are very, very important derivations, mathematical derivations. Okay, there's so many numericals may come in the numerical examination. Okay, this is a very, very important topic. Okay, this derivation is very, very important. Okay, how to find out the electric fields, how to find electrical voltage, how to find out the voltage sensitivity, charge sensitivity, any question may come. Okay, so that is a voltage derivation, okay, expression, mathematical calculation, and this is a piezoelectric crystal properties. Okay, it is known as the active as well as inverse transducers. We have understood that why it is called active, why it is called inverse. It's very simple because we are dealing with the piezoelectric transducers in daily life mostly. Okay, mostly it is used. Very common examples. Okay, so this is all about piezoelectric crystal transducers. Okay, and next class that I will be showing one numericals. Okay, one problem, analytical problems on piezoelectric crystal. Okay, and I will give you the 2-3 numericals for practice. Okay, piezoelectric crystals. So this is another examples of displacement. Displacement means actually displacement transduction means why displacement. Actually, you know, when some apply the force or apply the force, so it causes some deformation, body deformation, right? So it may some displacement. Okay, so that is called as a displacement transductions. Okay, so if you know some industrial diagram also is there. Suppose this is your, you know, this is the piezoelectric crystal. This is some input pressure is applied. So there is a crystal. Here is a crystal is there. Okay, so this is the crystal. This is the crystal. Okay, this is the crystal, and here you can apply one pressure sensor also. There is a diaphragm. There is a diaphragm. Okay, there is an application of the pressure sensors. So what is the function of these pressure sensors? Basically this pressure actually sense. This actually pressure the sense. Actually, this pressure sensor actually may be used for the limitation purpose. Because that what is the range of the pressure diaphragm or bottom proof, or that bottom tube, diaphragm, and another is there, that is bellows. Okay, there are three type of pressure sensors already you have studied. So you have know the different pressure ranges. So how much amount of pressure that is applying. So through this through it that you can measure it. Through it you can measure. Okay, easily you can measure how much pressure. Okay, so accordingly that suppose we are applying the bellows, or we are applying some diaphragm, you are applying some bottom tube. So then you can we already know that how much pressure should be applied on that. Okay, so otherwise it will not work. Otherwise, better that it will not work. So this is the application of the pressure sensors on piezoelectric crystals. Okay, there is some industrial applications. Okay, so you can apply anything, pressure sensors, distance sensors, transducers, other transducers on the crystals. Okay, so you have to think in this way. Okay, you have to think in this way. So this is all about the piezoelectric crystals property, and I think that it is clear to you all. It is clear to the piezoelectric concept, derivations, the basic properties. It is clear. Okay, fine. So